The idea of hypothesis testing is basically an extension of confidence intervals, where confidence intervals is a interval of two numbers where we believe a true parameter of a population exists. So what we're going to be doing now is we're going to make a hypothesis or an educated guess about a certain population, and we're going to perform some analytics to see how likely we are to be correct. So to do this, we need to know a couple of terms. We need to know what a null hypothesis is, for starters. A null hypothesis is basically an original statement about a population. For example, in this situation, we're making an educated guess about the population mean of a certain population. So we're going to say our null hypothesis is that our mean is equal to 45 units. The null hypothesis usually deals with a parameter being equal to a certain number. That number, the parameter can be the mean, or it can be the standard deviation, or it could also be a proportion. Okay, there's many different ways to state a hypothesis or a null hypothesis, depending on what we're talking about. So we have a null hypothesis, which is usually a parameter is equal to a number. Then we have an alternate hypothesis, which is denoted with HA or H1. When we're dealing with an alternate hypothesis, we're basically saying that the null hypothesis is not true. They can take many forms. We can say the alternate hypothesis is that our population mean is not equal to 45. We could say that our population mean is greater than 45. We may also say that our population mean is less than 45. Basically, we are taking our null hypothesis, which was the population mean was equal to 45, and now we're saying our population mean is not 45. So it can be less than, it can be greater than, or it can be not equal to. And we can do that with any parameter. We can use it with the mean or the population mean. We can use it for the population standard deviation, variance, proportion. It varies. Once we have our hypothesis and our alternate hypothesis, we begin talking about significance levels. Thinking back to when we did our confidence intervals, so if we had a 90% confidence interval, we would say our significance level, or alpha, was equal to 0.10. And again, the confidence intervals will vary. We have 90%, 95%, 99%, or they might ask for an 80%. It all depends. And the alpha, or our significance level, will change with the confidence interval. And basically, this is our threshold. So we're going to be testing our hypothesis based on our significance level. And to find the confidence interval, we need to use the test statistic. So thinking back to when you made the confidence intervals, depending on what parameter we were making a hypothesis against, would determine what kind of test statistic we used. So for proportions, we usually used a z-score. To find a population mean, or a confidence interval for the population mean, we usually used a t-table, or a z-score, depending if we knew standard deviation or not. And to find a confidence interval for the standard deviation, we used the chi-squared table. So there's different test statistics for different parameters, but they are all used to develop a confidence interval. When we are analyzing our hypothesis, there's two results we can have. We can reject the null hypothesis. So we have our null hypothesis and we create a alternate hypothesis. We create our confidence interval we perform some analytics, and we get a result. We can either analyze that result and say our null hypothesis was not true, which would be rejecting the null, or we can say we did not have enough data to reject the null. So we can either reject the null hypothesis, saying the null was not true, or we can say we don't know if it's true or not. Okay, so those are two options. We cannot say that the alternate hypothesis is true. All we can say that is the null hypothesis was either true or it was not true. So we can reject the null, or we can fail to reject the null. Which leads us to, there's two types of errors that people make. The first type, type 1, is when people reject the null hypothesis when the null hypothesis is true. So the first type of error is they reject the null hypothesis when in fact the hypothesis was true in the first place. Type 2, the second type of error, is they fail to reject the null hypothesis when the null hypothesis was false. So they can reject it when they were supposed to, or when they weren't supposed to reject it, or they can fail to reject it when they were supposed to reject it. These are both types of errors. So in this chapter, or in this idea of hypothesis test, we're going to be testing claims about different parameters of a population. The first type of parameter you would analyze is a proportion. These symbols should look familiar. P is our population proportion. Our Q is 1 minus that proportion. We have our P hat, which is our sample proportion. To analyze our proportion, we're going to use our z-score statistic, and this is how you find your z-score. So you would use this z-score to help you build a confidence interval, and when you build that confidence interval, you'll be able to analyze your null and alternate hypothesis. We could make test claims about means, where we have our sample size again, our sample mean, our sample standard deviation. For this test statistic, we would use a t-table, because usually if we're trying to make estimations about a mean, we don't know the standard deviation. So if you don't know the standard deviation, you can't use a z-score. So a lot of the times we use a t-table when we're making claims about a mean. Again, these test statistics will help you build a confidence interval, and then you can use that to test your claim. And last, we have making claims about standard deviation or the variance. We are very familiar with this notation. To test a claim about standard deviation or variance, we use the test statistic of a chi-squared. The chi-squared is a different graph than the normal distribution, but it's a similar idea. We're going to use these statistics to build confidence intervals and use those confidence intervals to test claims about data. So once we determine the population parameter we are analyzing, that will tell us what kind of curve we are using. So if you are analyzing a standard deviation or variance, you're going to use the chi-squared model. The other ones, you're going to be using a normal distribution model. And what those test statistics will give you, depending on your confidence interval, those test statistics will give you a location on the normal curve. So for example, let's just say our test statistic lands here. And when you look up the test statistic on your appropriate table, so if it's a z-score, you're looking at a z-table. T-score, you're looking at the t-distribution table. That will give you the total area to the right of that value. To the left of that value. Okay, but what we're concerned about is our p-value, or the area to the right of that statistic. So depending on the significance level you have, so if you're looking for a 95% confidence interval, this test statistic will have 95% of the data over here. and we have a 5% chance that we land in this tail. So a 5% chance for that threshold is unlikely. So it's something, if we collect data and our data lands in this area, that's cause for concern because we thought this was incredibly unlikely. And here we are, we just collected data and it happened. So we have our test statistic, we have our confidence interval, we have our alpha level. So if we calculate our p-value, it's important to know that p does not stand for population, it stands for probability. So if our probability value is less than our alpha, or less than our significance level, so our probability of that event happening is smaller than our significance level, that means our p-value is inside that tail, or inside that area of concern. So we would say we are going to reject the null. Again, if our p-value is inside this problem area, that means it was extremely unlikely for that to occur, and yet it did occur. So since something very rare happened, that's cause for concern. So if our p-value is smaller than our alpha, we reject the null. If our p-value is greater than our significance level, that means our event is occurring in this area, which was in our confidence interval. So if our event is occurring inside our confidence interval, that is not cause for concern, so we would not reject the null, or we would fail to reject the null. Okay, so again, looking at the normal curve, and this is the same idea if it was a chi-squared model, just the curves look different, but it's the same exact idea. If we have our test statistic, this test statistic will give you the area under the curve to the left. We're looking at our p-value. If our p-value is inside this area, meaning it is less than our alpha, that means it's cause for concern because something that we thought was going to be incredibly unlikely has occurred, which is not a good thing. So in the event that our p-value is smaller than our alpha, we reject the null. We say the null hypothesis was incorrect. And if our p-value is greater than our significance level, that means the event that we found is occurring in this bubble, which is not a cause for concern. So that means we are not going to reject the null hypothesis.